Um, you will notice that I'm going to do the examples in a slightly different order than what they are on the example sheet that I uploaded to D2L. I've just, because of like one extra technicality to one problem, I've moved it to be the last one we look at today. So we're still talking about ANOVA, in other words, trying to determine in a statistical sense whether several different treatments or several populations have means that can all be assumed to be equal, or if there are differences between some or all of the means. And so going through the ANOVA procedure and implementing the F-test, that allows you to determine whether they are all equal or whether there is some kind of difference that is manifesting in the data. And if you find a difference, then we have to move on to the Tukey procedure that was discussed in yesterday's video to determine which of the treatments or populations differ from one another. So today's examples are going to lean into implementing the Tukey method. It does come with the following caveat. It is a different method than the F-test. So you can sometimes get inconsistencies. It is conceptually possible that implementing the ANOVA and calculating F observed and then the corresponding p-value tells you that there is a difference. But then you go and do this what I'll call post hoc comparison, the multiple comparison procedure, and you don't find any differences between groups. That doesn't happen often, but it is technically possible. And the flip is also true. You wouldn't necessarily do this, but your F-test could tell you that there are no differences, in which case it doesn't really make sense to go and do Tukey. But if you were to go and do Tukey, you can sometimes then find groups that differ significantly, even though the ANOVA said they didn't. And that's just because these two procedures, even though you're calculating them using the same data, they're based on different principles. And so the data sometimes aligns with one of the principles better than one of the other principles. And so they have the potential to give slightly contradictory results. So that's the caveat here. Now let's jump in and look at this first example. An experiment was carried out to compare 5 different brands of oil filters with their ability to capture foreign material. So we want to compare these 5 brands of filters, and we selected 9 filters of each brand and did an experiment. And we have the results of, how much foreign material they captured. The ANOVA table's already been completed. We still want to implement the ANOVA to determine whether there is a difference, say, at the 5% level. And if our null hypothesis is rejected, then we're going to move on to Tukey to determine which of the brands differ from one another. So in this case, our null hypothesis, I'll just do this for completeness, is that the 5 filter brands on average capture the same amount of foreign material. And our alternative says there's at least 2 means you can find that are different from one another for some pair I and j. So all the alternative is saying there is at least 1 pair of filters that capture on average different amounts of foreign material. We're then to implement our F-test, we want our degrees of freedom, but that's already part of what's calculated in your table. So you already have those 2 degree of freedom numbers, which means you can immediately go to calculating your p-value, which relies on you using the FCDF function, lower bound of 0, upper bound the 37, sorry, I'm cramming stuff in there a little bit. what you're going to find when you go and evaluate this specific p-value is that whether you're rounding to 3 or to 5 decimals, it'll be very nearly 0. Like it is 0.00000001. So a p-value in this instance of 0 is less than our alpha level of 5, and so we reject the null hypothesis, which means our sample evidence suggests at least 2 filter brands differ on average. But we don't know which. So now we want to go and implement Tukey to make that determination. So the Tukey procedure, firstly, has us sort the sample averages. So these sample averages, we want to go and sort them from smallest to largest. So if I do that, the ordering is 13.3, 13.8, 14.3, 14.5, and 14.6. And that corresponds to, I guess I'll use B for brand. Brand 1, brand 2, this was brand 5, the 13.8 was brand 3, and the 13.3 was brand 4. So one thing that we do know, if nothing else, we would probably conclude that brand 4 and brand 1 differ from one another because they're the furthest apart, but we want to make a more specific determination than that. So we need to calculate the relevant value from the studentized range distribution. We need to go and find the value Q of alpha, M, and nu. So this we find in our studentized range table. Alpha in this case is 0.05, and then I actually believe I omitted giving the formulas for the degrees of freedom when I was recording the video yesterday. So the first degree of freedom value, M, is equal to I, and the second degree of freedom value, nu, is equal to I times j minus 1. So they're almost the same as for the F-test. If you're doing an F-test, you're actually doing I minus 1 for the first degrees of freedom, and for the second one, I times j minus 1. So the second value is the same. The first value differs by 1 digit. So in this case, we have 5 degrees of freedom for the first value and 40 degrees of freedom for the second value. So I've uploaded the studentized range table to D2L, and it's also in the back of your book. You'll see here columns correspond to first degree of freedom value. Rows correspond to the second degrees of freedom value. And then there's a separate column for alpha, and it only gives you alpha 0.5 and alpha 0.1. So in this first example, we know M is equal to 5. So that's the row we'll look at. We know our second degrees of freedom value is 40. So we'll read from that row. And we want it for alpha equal to 0.5. So that's the specific row we're looking at. And so our Q value is 4.04 in this case. So our Q value is 4.04. Now we calculate the width of the confidence interval. Let me check just another question here. So I have a question about interpolation, and yes, we'll have an example today where we touch on interpolation. So if you'll hang on to that question, we'll actually circle around to that a little bit later. So our formula for W, which is the width of the confidence interval, is given by the Q value times square root of mean square error over J. And just in case you didn't watch yesterday's video, the reason I'm talking about a confidence interval here is underlying this whole Tukey procedure is the idea of constructing pairwise confidence intervals for each possible pair of means that we can construct. But in implementation, we don't actually go through that construction. We just assess whether the sample averages are far enough apart that they wouldn't be in the same confidence interval. And that's what this width tells us. If they're this distance W apart, W or more, they wouldn't have overlapping confidence intervals. So in this case, our width is given by 4.04 times the square root of, in this case, if you read the table, mean square error is pretty small, 0.088, and J is the number of observations per group, which in this case is 9. So if we evaluate this, I'm just going to round it here. It's actually 0.399, but I'm just going to round the width value to 4. So now we want to go and assess how far apart our different sample averages are. So the first two have a distance of 0.5. Then we have a distance of 0.5 again. Then we have a distance of 0.2, and finally we have a distance of 0.1. So what the Tukey procedure says is you are going to underline values that are closer than W from one another. So brand 5 and brand 2 only differ by 0.2, right? So I would go and underline. And then I would ask myself, well, how far is brand 5 from brand 1? Well, that's still just a distance of 0.3. So they're still close enough together as well. Brand 4 and 3 are more than this distance apart. Brand 3 and 5 are more than this distance apart. But then all the other brands, 5, 2, and 1, the distance between their averages is less than 0.4. So what this tells us then in summary is that there's no evidence that brands 1, 2, and 5 differ from one another. They're all close enough together that we don't see a difference. But brand 4 is pretty distinct, brand 3 is pretty distinct, and those are also distinct from the group. So I can, in this case, at least almost create groupings, right? I can say there are 3 groups that differ. Group 1 is just brand 4. Group 2 is just brand 3. And group 3 is brands 1, 2, and 5. Now, we'll see, we don't always have this kind of clear delineation, but in this case, we do. Let's see, I have another question here. And so I have a question about whether it matters how you order them. The only time the ordering matters is when you're ordering the sample averages, what we're doing here at the start. Here you have to sort them from smallest to largest. But once you've identified where the differences are, it's kind of arbitrary what you label them. So these groupings that I created here, I could have said group 1 is brands 1, 2, and 5. That doesn't matter. Just the distinction of how you group them, that's the important thing, figuring out where the differences are. You don't even have to go and write it as groupings, as I've done specifically. You can just, in a sentence, write out and tell me which ones differ from one another. So an interpretation here potentially would be, we've identified 3 brands which seem to have superior performance because they're capturing more foreign materials. So if you want to put a good brand in your car, you can use brand 1 or brand 2 or brand 5. Statistically, we don't see any evidence of differences between them. But they all seem to be superior to brands 3 and brands 4. Like if you go to the store though, and you can't find brand 1, 2, or 5, you would rather buy brand 3 before you buy brand 4, because 3 is still significantly better than 4 at the 5% level of significance. So that's how we would interpret these values. Are there any other questions about this example? Yeah, so your final answer for a problem like this will be something to the effect of either describing in a short paragraph which groups differ from one another, or creating that grouping. Like I would like to see this analysis where you underline and don't underline to identify the differences, but you have to go one step beyond that, either create groupings, and we'll see it's not always possible to create neat, clean groupings. I think we'll see that in our next example. But if that's not possible, you kind of have to write out a couple of sentences telling me what the differences are that you're observing. So let's look at this next example. Here we have data collected by a biologist who wants to see how ethanol affects sleep time. And so 20 rats were given oral injections of ethanol per body weight, and then their REM sleep was measured for a 24-hour period. So in this case, we have 4 different ethanol treatments that get applied, and we had 20 rats equally divided between the 5 groups. So J will be 5 rats per group. So first thing we want to go and do is just evaluate whether or not we're going to reject our null hypothesis. So to do that, we need the p-value. And that's going to be 1 minus the FCDF. We know our F observed value is 21.09, and we have 3 and 16 degrees of freedom, right? We just get those from the table. And the lower bound here, of course, was 0. So this is another instance where if you go and calculate this p-value, it is essentially 0. So our p-value here is less than our alpha level of 1%, and so we reject the null hypothesis. So we find evidence of a difference. But the ANOVA doesn't tell us where the difference is. We want to go and figure out where which treatments in this case differ from one another potentially. So we're again going to order our means from smallest to largest. So in this case, 32.76, then 47.92, 61.54, and 79.28. So this is treatment 1, treatment 2, treatment 3, and treatment 4. So that's what we'll use to assess whether the means are far enough apart to be considered different. But to do that, we again need to go and implement this, or do this width calculation. So for the studentized range distribution, our alpha in this case is 0.01. Our first degree of freedom value is the number of groups, in this case 4, and our second degree of freedom value is I times j minus 1. That's the same as second degree of freedom value in the table. So this gives us the ability to go and look up the appropriate Q value. Flipping over to my table, in this case, let me use a different color. 4 degrees of freedom and 16 degrees of freedom at 1% level. So my studentized range value this time is 5.19. So now I'm going to calculate my width. It'll be my Q value times mean square error over J. So 5.19 times the square root of, again, mean square error I'm just taking from the table. And so when I do this calculation, my width is 22.38. So anytime the treatment means are further apart than 22.38, that tells me that I've found a difference. So let's go and evaluate how far apart these are from one another. So from treatment 4 to treatment 3, the difference is 15.16. From 3 to 2, the difference is 13.62, and finally from 2 to 1, it's 17.77. So firstly, what you'll notice is, at least in the ordering, if you're just comparing adjacent treatments to one another, we're not immediately detecting differences. So treatment 4 and 3 are within the width W from one another. But treatment 4 and 2 are not. Like, that total distance is close to 29. So we wouldn't extend the line to go to treatment 2. But if we just look at 3 versus 2, those are close enough together to not be different. And finally, 2 and 1 are close enough together to be different. So this is where the interpretation can get a little interesting, right? We don't see a difference between treatments 3 and 4, for example, but we do see a difference between treatments 2 and 4. So the post hoc procedure here, or this multiple comparison, it can sometimes be difficult to interpret because we get seemingly contradictory results. The best way to fix that in practice is to go and collect more data, get a larger sample size, rerun the analysis. But what we conclude in this instance is there's no difference between treatment 3 and treatment 4. There's also no difference between treatment 2 and treatment 3. And there's also no difference between treatment 1 and treatment 2. But all other pairwise comparisons are significantly different. Let's see what the question here is. And yes, so the question is whether the blue line is a visual representation of the range. That's what it's trying to get at. You underline sequential mean values as long as their width from one another is less than the W. So I would start at, for example, treatment 4 and say, when I move from 4 to the next mean, which in this case is treatment 3, is the width less than 22.38? Yes. Is it still less than that going to treatment 2? Like, would I still connect? And the answer is no. There's no reason to keep that line going. The reason the interpretation on this one looks a little bit different than on the previous question, if I scroll back up, in the previous question, we got 3 very clean groups. There was no overlapping lines, right? And so we could create 3 distinct groups of, in this case, brands of filters and say, this grouping is different from this grouping, is different from this grouping. We could say, no overlap, we can create 3 distinct groups. That's a really nice, clean conclusion. The example we're currently on, this is kind of a nightmare for someone doing an experiment because they're finding that adjacent treatments do not appear to be different. Like, logically, there's an inconsistency, right? If I say, oh, treatments 1 and 2 appear to be the same, and treatments 2 and 3 appear to be the same, but 1 and 3 appear to be different. Like, what do people do with that information? It's kind of messy to interpret. So we can highlight where we find no differences, and then we can say all other pairwise comparisons appear to be different. So here you just have to carefully articulate what you're seeing, especially if you're getting an inconsistency. There's no like perfect recipe for what a solution should look like. So we have one more example here to look at. Problem 10.4, and this is just picking up from 10.2. So we've already done the ANOVA analysis. We found a p-value of 0.006, which is significant at the 1% level. So we found evidence of a difference. But we now want to implement Tukey's procedure to determine which of these treatments differ at the 1% level. The one piece of information I forgot to copy over from the previous problem was just what the mean square error value is. That's 37.926. And that's just that was calculated in 10.2. So for Tukey procedure, again, we're going to start by ordering our treatment averages. So smallest is 10.5, then I guess these were already conveniently labeled in that specific order. So this is just treatment 1 through 5, ordered from smallest to largest. Now in this case, for our studentized range value, alpha is 1%. First degree of freedom I is, in this case, number of observations per, number of groups, which is 5 groups. Our second degree of freedom value is I times j minus 1, which is 5 times 9, that's 45. And So we want to go and find the Q value of 0.01 with 5 and 45 degrees of freedom. So here we flip over to our table. Great, 5 degrees of freedom. And so we know we're using this column. Oh, oops, no 45 here. But let's just see what's going on here. The two adjacent values we can evaluate at 1%, 4.93 and 4.82. In fact, if you compare all the values at the 1% level, you can see that they're decreasing as the number of degrees of freedom increase. So ideally, you'd want to do a little bit of interpolation here, but I'm okay if you just eyeball the difference. So we want 45, right? 45 is going to be a lot closer to 40 than to 60. So we need to use a value that's closer to 4.93 than to 4.82, but it's somewhere in between them. And so I think I'm certainly going to be lenient here about what value you use, as long as you show me that it's between the two values and it's closer to one than to the other. So, you know, extreme scenario, you can go and average them, 4.93 plus 4.82 divided by 2. Their average is 4.88. It needs to be closer to 4.93, or sorry, it needs to be on the 4.93 side. It needs to be higher than this to be close to 4.93. So if you sit there and you remember the formula for linear interpolation, feel free to use that. But just eyeballing and saying, oh, this will be approximately 4.9, that should work in this situation. So there's our Q value. And that was the only add-on to this problem, is not being able to read an exact value from the table. So now we can calculate our width. So in this case, 4.9 times square root of 37.926 over 10, which is 9.54. So let's go and figure out how far apart our treatment averages are from one another. This is 4.3. This is 0.9. This is 0.3. And finally, 5.6. And have a question about whether there'll be a situation where level of significance is not 1% or 5%. I will not be that cruel with this. So degrees of freedom may pose an interpolation situation to you, but these ANOVA tests, just because of the way the table is constructed, I will always ask them at the 1% or the 5% level. So you don't have to worry about interpolating over the significance level. Okay, so now we want to determine which of our groups are within this width of one another. So definitely treatment 1 and 3. In fact, just a small jump to get to the next treatment, just a small jump to get to the next treatment. So no difference here between treatments 1, 2, 3, and 4, because from treatment 1 to treatment 4, that total span is still less than the 9.54. Now, let's start on the other side. Treatment 5 does not seem to be different from treatment 4, and not different from treatment 3, and not different from treatment 2. So here again, we have this overlap. We kind of have this logical inconsistency. So what we would say in this case is no evidence of a difference between treatments 1, 2, 3, and 4. Also, no evidence of a difference between treatments 2, 3, 4, and 5. But like the only difference you can identify here, right? Treatment 1 and treatment 5 do not seem to overlap. So we highlight where we don't see differences, and as opposed to the previous case where I said all other pairwise comparisons are significantly different, in this case, there's only one pair that's not captured by what I've already said, and that's comparing treatments 1 and 5. They appear to be significantly different, but I'm not detecting statistically any other significant differences. Now, clearly, in the real world, this cannot be true, right? Either the treatments differ or not, but the setup of this experiment, the sample size is too small to let us detect which of these other, what I'll call non-differences really should be differences. We just don't have the ability to detect those because our sample size is too small. And the only way we can fix that is by collecting more data.